Hello students, let us continue our discussion on real analysis. So we had done the field axioms, and then we have derived that the identity element, that is the zero element in R, is unique. We have also seen the additive inverse of each element is unique. Okay. So today also we will derive several properties which we have been using since our childhood without any proof, right? So let us try those properties, right? So let me list that this is an exercise, or you may write it as a theorem also. If or let me write it this way, show that a dot 0 is equal to 0 for all a inside R. Okay. Right, so this we did not list this as a field axiom. Okay, we are deriving it using the field axioms. It means any real number multiplied with 0 is 0 only. Okay, so remember what was the property of 0? We had just listed one property of 0. 0 is a number which satisfies a plus 0 equal to a for all a inside R. Okay, this was the definition of 0 that we gave, right? So we will see that using this definition we can actually using this definition and the uniqueness of 0, we can just show this part, right? And maybe the left cancellation law which we had already done. Okay. So a dot 0 equal to 0 for all a inside R, right? So we have a 0 plus 0. Okay, 0 plus 0 is equal to 0. Okay, this is by property of this 0 element. 0 plus 0 equal to 0. So from there, if I just multiply with this a, this will be a into 0 plus 0 equal to a into 0, right? So from this side I can use the distributive property a dot 0 plus a dot 0, and in this side I can just write a dot 0 plus 0, because I am using this property here. Okay, a plus a can be written as a plus 0. So a dot 0 is also an element in R, so it can be always written as a dot 0 plus 0, right? We can write it that way. And then you see we can use the cancellation law. Okay, we have a plus b equal to a plus c. This will imply b equal to c. We can use the cancellation law. Okay, so if you don't want to use this cancellation law, means ultimately you will be using but say if you don't want to write by cancellation, so then you can do it directly. What you can do is you can multiply you can add the additive inverse of minus the additive inverse of a into 0, okay, on both sides. So this part will become, so I'll show you both the ways, if you both the ways are correct. Okay, so one way is, say the first way is I just use the cancellation law, because I have the same elements here. So using the cancellation law, a dot 0 is equal to 0 by left cancellation law. Okay, right? And another way is, second way is, so here already I have proved a dot 0 is 0. Second way is, from this step you come to this step, that you can take minus of a dot 0 plus a dot 0 plus a dot 0. This is equal to, so this you can come from not from this step, you can come from the earlier step as well. You can come from this step also. Okay, from this step. So this is actually minus a dot 0 plus a dot 0. Okay, so means I won't write this Okay, just let me increase one line. So from the earlier step, the second way is I'll just write a dot 0 plus a dot 0 equal to a dot 0. Okay, and then I'll just add minus of this additive inverse of a dot 0 on both sides. Okay, this is a dot 0 plus a dot 0 equal to minus of a dot 0 plus a dot 0. Okay, so once I do that, this is minus of a dot 0 plus a dot 0 by associative property. Okay, I can use the associative property here, plus a dot 0. This will be equal to 0 here, right? This one is 0, and minus of a dot 0 plus a dot 0, that is also 0. So 0 plus a dot 0 is equal to 0. So 0 plus a dot 0 is again a dot 0. So a dot 0 is 0. Okay, so you can do it this way also, no problem. You can do it this way by using left cancellation law, or if you want to just derive it from the basics, you can just do it this way. Okay, a dot 0 is 0. So we have proved this, right? So any element, any real number multiplied with 0 gives you 0 itself. Okay, let us try another one. Another one is, say, so that is actually uniqueness of reciprocals. So we have already done that, so that's another version. If a comma b belongs to R and a not equal to 0, with a dot b equal to 1, okay, then if if b is such an element which satisfies a dot b is 1, then b is nothing but the reciprocal of a, 1 by a, then b equal to 1 by a. Okay, so how do you do that? Solution is, since a not equal to 0, so by our field axioms, this 1 by a is an element in R. Okay, 1 by a is an element in R, and so given 1 by a is an element in R, and what does it satisfy? It satisfies that a dot 1 by a equal to 1 equal to 1 by a dot a. Okay, this is the property that it satisfies. So given this a dot b equal to 1, so from there we can write a dot or 1 by a dot b equal to 1 by a dot 1. Okay, we are multiplying both sides by 1 by a, and then I just apply the associative property of this multiplication. So this will be 1 by a dot, so here you just write by associative property. Okay, associativity of what? Of multiplication. Okay, so 1 by a into 1 is 1, so 1 dot b equal to 1 by a. So from there b is same as 1 by a. Okay, so if we have any real number b which satisfies a dot b equal to 1, then immediately b is nothing but 1 by a. Okay, then another exercise, you can try that, this one, if a comma b belongs to R and a dot b equal to 0, means if the product is 0, then what do you write in your school days, or since your school days we have been writing this a dot b equal to 0 means either a is 0 or b is 0. Okay, so product of two real numbers is 0 only when either at least one of them is 0. Okay, so then either a equal to 0 or b equal to 0. See, we are just proving all the fundamental things that we have learned, or we have already used, we have been using. Okay, so using the field axioms, we have just listed 10 or 11 properties of these real numbers, and using those properties we are proving all this. Okay, so that we can apply these properties in the later part of real analysis. Okay, we don't get stuck anywhere. Okay, all these properties are satisfied. Okay, so what do you have? So given this is given to us a dot b equal to 0. Okay, so if a is 0, then what happens? Then we don't have to prove anything, no? Then we are done. Okay, now there is nothing to prove, because we need to prove either A is 0 or B is 0. Okay, so if initially we already get somehow that yeah, A is 0, then we don't have to prove anything. Okay, our statement is correct. So then we are done. So let A not equal to 0. So let us see what happens when A not equal to 0. So what is our intention? If A not equal to 0, we have to show that, we have to conclude that in that case B has to be 0. Okay, so let A not equal to 0. Then by our field axioms, 1 by A is an element in R, right? A is non-zero, then 1 by A is an element in R, right? And it satisfies A dot 1 by A equal to 1 by A into A. Okay, so this is satisfied. So A dot B equal to 0 will imply that I can multiply both sides by 1 by A. So this is a 1 by A into A dot B. This will be equal to 1 by A into 0. So here I'll use associative property. 1 by A into B equal to 1 by A into 0. Already we have proved any real number multiplied with this is equal to 0. Any real number multiplied with 0 equal to 0. So the reason we will write it this way: x dot 0, since here already A is there, we are not confusing with this A. So let us write x dot 0 equal to 0 for all x inside R. Okay, this we have already proved. So here associative property. So here we are using two properties: associative property and this property. Okay, so 1 by A into A is 1, so 1 dot B equal to 0. But what is 1 dot B? By our field axioms, 1 dot B is always 0. 1 dot B is always B. So B is equal to 0. Ultimately we have shown. So either A is 0, or if A is non-zero, then B has to be 0. Okay, so this is another property. Then another exercise you can try, that if A dot A and B are A plus B equal to 0, let A comma B belongs to R with A plus B equal to 0. Okay, then B has to be actually minus A. Okay, so this is also the uniqueness of inverse additive. We have already shown the uniqueness actually. So you can do it using the field axioms. Okay, so since A belongs to R, so minus A is an element in R. Okay, and what does it satisfy? A plus minus A, this is equal to 0, equal to minus A plus A. Okay, this is satisfied. So given A plus B equal to 0, so how do you show this? So I just add minus A to both sides, right? So this is equal to minus A plus 0. So this one is minus A plus A by associative property plus B equal to minus A plus 0 is minus A. So what is minus A plus A? It is 0. 0 plus B equal to minus A. So 0 plus B is again B. So B equal to minus A, right? So whenever any element B satisfies A plus B equal to 0, that element B has to be minus A, that is additive inverse of A. Okay, so always remember, what is this minus A? Minus A is actually additive inverse of A. Additive inverse of A. So this exercise is also another way of saying that additive inverse is unique. Means whenever there is an element B which satisfies this, okay, B has to be minus A. Okay, then another one, let us try, which we have also done in our school days. So show that minus of minus A, okay, minus of minus A, this is always same as A. Okay, means additive inverse of minus A is A itself. Okay, additive inverse of minus A is A itself. Okay, so how do I show this? So we have minus A plus A will be equal to 0. Okay, this is already there, right? So what I do is I add additive inverse. So since minus A is also an element in R, right? Since minus A belongs to R, so it will also have additive inverse. Okay, so its additive inverse. Okay, its additive inverse additive inverse. So what will be the symbol for its additive inverse? It will be minus of minus a. Okay, additive inverse of x is minus x. So additive inverse of minus a will be minus of minus a. Okay, so at this moment I do not know whether minus of minus a is a or not. Okay, I just have to prove it. Okay, so this is also, I just know that this is also an element in R. Okay, so so minus a plus a equal to 0 will imply that what I do is I add minus of minus a to both sides. Okay, minus a plus a equal to minus of minus a plus 0. Okay, and then I use the associative property here. So this is minus of minus a plus minus a. Okay, this plus a equal to minus of minus a. Okay, because this added with 0 is the element itself. Okay, but what is this? By property, by our field axiom, this is 0. So 0 plus a equal to minus of minus a. Okay, so this means a is the same as minus of minus a. Okay, right. So we have already proved this. A is equal to minus of minus a. Right. Okay, so let us try another one. This property minus 1 into a. Yeah, now what happens if we multiply this? Show that minus 1 multiplied with a, it actually gives you the additive inverse of a. Okay, for all a inside R. Okay, minus 1 multiplied with a always gives you additive inverse of a. Right, so the solution is, you start with this one, minus 1 we have. So what is minus 1? Minus 1 is additive inverse of 1. Okay, so minus 1 plus 1 equal to 0. Okay, so this one I just multiply both sides with this a. So minus 1 plus 1 dot a, this will be equal to 0 dot a, because these two are the same elements. So I can write this as minus 1 dot a plus 1 dot a, this is equal to 0 dot a, already we have shown this is 0. Okay, so minus 1 dot a plus a equal to 0. Okay, so now also you can do it two ways. First way is just apply uniqueness of additive inverse. Okay, so by unique, so this is an element which satisfies, means we have already done that, no? This one, an element b which satisfies a plus b equal to 0, then b has to be minus a. Okay, so it's something similar to that. So this minus 1 into a is an element which satisfies minus 1 into a plus a equal to 0. So this minus 1 into a has to be additive inverse of a. Okay, so first way is you do it this way. So minus 1 into a has to be minus a. Okay, by uniqueness of additive inverse, you can just write it this way, uniqueness of additive inverse, additive inverse. Okay, right. And the second way is, you can do it the second way also. First way is this, second way is what, you just add minus a to both sides. Okay, second way is this one, plus minus a will be equal to 0 plus minus a. Okay, so we can do it this way, right, and then apply associative property. So it's minus 1 into a, sorry, it's minus 1 into, okay, it's minus 1 dot a plus minus a. Okay, a plus minus a will be equal to minus a. Okay, so from there minus 1 dot a plus 0, this is equal to minus a. So from this minus 1 dot a equal to minus a. Okay, so you can do it this way also, or you can just use, because we have already shown that additive inverse is unique, so you can just conclude it from this step as well. Okay, so no need to extend it up to this. So you can just write by uniqueness of additive inverse, minus 1 into a is same as minus a. Okay, so this is another problem. So let us try another problem. Let us try this problem. Yeah, minus 1 into a is minus a. Already we have seen. Another very important thing which you have already used always, show that minus 1 into minus 1. Okay, this is always 1. Right? If we multiply the additive inverses of 1, we get 1 itself. Right? So how do you show this? So this also will follow from this property. We have minus 1 plus 1, this is equal to 0. So from there you multiply both sides by minus 1. Okay, this is equal to 0. So from here minus 1 into minus 1. Okay, plus minus. So here I am applying the distributive property. Okay, sorry, this one also, this will be minus 1 dot 0. Okay, so this is 0. So by distributive property, okay, right. So from this I can write minus 1 into minus 1 plus, what is minus 1 into 1? It's minus 1 only. Okay, by using the definition of this unity element. Okay, and then what I can do is I can just add my 1 to both sides. Okay, so from uniqueness of inverse also it will follow, because already we have shown that minus of minus a, this problem we have shown minus of minus a is a, right? So that from there also it will follow, but we can do it this way also, minus 1 into minus 1 plus minus 1 plus 1. Okay, so what I am doing is I am adding plus 1 to both sides, equal to 0 plus 1. Okay, so then apply associative property. So it's minus 1 into minus 1 plus minus 1 plus 1 will be equal to 1. Okay, so it's minus 1 into minus 1 plus 0 equal to 1. So this is actually minus 1 into minus 1 equal to 1. Okay, so we have proved it. So minus 1 multiplied with minus 1 is always 1. Okay, so please try to revise these things. And some other properties are also there. Let a comma b belongs to R. Show that minus of a plus b is same as minus a plus minus b. Okay, so this also we can show it using a uniqueness of additive inverse. Okay, so means what I have to show? I have to show that additive inverse of a plus b is this. Okay, so what I can do is I can just calculate what is the sum of these two, minus a plus a minus a plus minus b plus a plus b. Okay, let us calculate this sum is equal to what? Equal to, I can apply the associative property here, minus b plus a plus b. Okay, so I can use this associative property. So here I have used associative property. Okay, so in exam do not use shortcuts. The important thing is here is you have to show that you have understood what are the properties we are actually applying here. So it's minus a plus, again I can use commutative property here. Okay, b plus a, because I need to use this minus b plus b somewhere. Okay, commutative property. Okay, so from this I can write minus a plus, this is actually minus b plus a, again I have used associative property. Okay, so this is minus a plus 0 plus a. Okay, so ultimately it's minus a plus a, so that is equal to 0. So ultimately I have got this plus a plus b, this is equal to 0. So by uniqueness of additive inverse, we have minus of a plus b is actually same as minus a plus minus b. Okay, so this we have already shown. This is by uniqueness of additive inverse.